So, hello everyone. In the previous lecture, we have discussed about total stress analysis. And remember again, the total stress analysis is to analyze slopes under undrained conditions, not drained conditions. For example, if there is an embankment which is soon after construction, the water has no time to disappear from the embankment. Therefore, the stability should be considered with respect to total stress analysis. But what happens when the seepage starts to occur and there is a drain condition? And also, for example, if you take a natural slope which is under, normally there is a groundwater table, there is a groundwater flow or seepage. So these conditions should be analyzed using effective stress analysis. Why? Because we have to consider the effect of pore water pressure. For example, here this, let's say this is a water flow, or a groundwater table. So as a result of this water pipe, there will be a effect of pore water pressure at the bottom of the slice. You can see. So there will be an effect of pore water pressure at the bottom of the slice. So as a result of this, you can imagine that what will happen to the components of the weight components of the slice, especially this N. So what will happen is due to this effect of water pressure, we know that N is the total normal force. So if we write the forces, N is the total normal force, but the effective normal force will be something like N dash. We know the effective stress principle says sigma dash equals sigma minus U. So if you multiply this by area, or in this instance it is length, right? Because we always consider 2D image with 1 meter or 1 unit length into the canvas. So if you multiply this by L, get sigma dash become force N dash, and this become N, and U should be multiplied by L. So we can say N dash should be UL, sorry, it should be U, right? So that is the effect of pore water pressure. So therefore this effect should be contained in our factor of safety equation. You can see no longer it is not N, it is N minus UL. UL because of the pore water pressure U, and L is the length of the base of the slide, right? And so since we know these L values, we should know these L values. This in the previous equation was something like this. That is CR theta plus N and P divided by sigma. This should be sigma T. But now since we need to use L, we can show this CR theta, which is the total length of this curved surface, which is is a collection of all these L values. So that's why this become C into L and sigma, that means for all the slices, right? Same thing. And the other important thing is that the parameters, you can see the parameters are not total stress parameters. These are not undrained parameters. These are drained parameters. If you go and look at triaxial test we discussed in last year, that we have discussed about drain parameters or effective stress parameters. So we denote them as C dash and P dash opposed to C and P in total stress analysis. So you can see, so the major differences are the parameters we use and also how we consider the effect of normal force, right? So those are the things that we need to be focused on when we assess the factor of safety of a slope under effective stress analysis. And the other thing, you may wonder how we can find U, right? This U. Now it depends on let's say this okay. So this is an example, an embankment. You can see here is water, this part, the water here. This is like a earth dam, right? We have discussed about earth dam in flow nets, right? And we also know, I think we did an example in CW also, when the seepage occurs within earth dam, and likewise. Now the important thing is, if you want to find the pore water pressure, right, on average at the base of the slice, right, say this U, the base of the slice, if the water level is this, if we take this as the height that determines pore water pressure, it is wrong, right? Why? Because we don't know it is the correct way. The correct way is to analyze the flow net, right? Flow net, right? Because what we need is equipotentials. Equipotentials. If we follow equipotential, then term equipotential means along this line, pressure head plus elevation head is the same, right? Pressure head plus elevation head is the same. That means total head is the same. You know, total head is equal to pressure head plus elevation head. Right? So this is an equipotential, right? This is a flow line plus flow line and equipotential, right? Therefore, we know along this line, this should be a constant, right? These two are constant. For example, at the top, we know pressure head is 0. Pressure head is 0. There is elevation, right? But as we move along this line, we can see there will be an elevation difference, right? So let's say at this point there is elevation difference. Let's say delta H, delta H elevation difference. So actually, what happens is elevation drop, right? There is a reduction of elevation, right? So this, let's say this reduction of elevation, delta H E, and as a result of this, we can see now the effect of water is there at this point, right? Due to this water above that point, that creates a pressure, right? Pressure. So we know this reduction of elevation head, should be equal to the gain of pressure head, because ultimately pressure head plus elevation head should be at same value, right? This we have actually discussed in your second year under soil permeability, so, and also in flow nets, right? It's, just to remind you what we are doing here, because taking this water height is not correct. What we have to do is take the, for example here, what we have to do is draw the flow line, draw equipotential to the flow line, and then find out that vertical height. Right? Let's say this vertical height is HW. For this case, take, so this is your, this height is HW. Right? So pore water pressure U should be this HW into gamma W, that is the unit weight of water. Right? So that's how we can find for water pressure at the bottom of the slice, right? Especially at the middle of the slice, right? Middle of the slice. So taking a value at the middle of the slice will be considerably accurate to assign them in the slope stability analysis. So let's look at an example. And do this again using a tabular form, right? So in this handout there is a exercise, right? So the exercise is given. So these are the exercise values, gamma, C dash, T, R, theta given, and also with this table, right? So you can see, and here you can see the HW value, right? And slice number, alpha, area, W, and the width of the slice is given. Right? You may wonder why we need width of the slice, because we take this slice, right? To calculate the effect of forward pressure, we need this L, right? L. So the width of the slice means this B. Right? B. So if I draw the slice again, you get something like this with the alpha, and the width of the slice is B. What we need is this length L, right? So you can see therefore this angle is alpha, so this is your L. So we know this L cos alpha, right? L cos alpha is equal to B. Therefore L is B over cos alpha. So if you know B and alpha, you can easily find L. Right? So you can see an HW is given to find U, right? So you can take gamma W same as 10 kilonewtons per cubic meters, right? And so again we need to make a table, right? We need to make a table in order to find the respective parts of the equation, this, right? So we need to find n dash, which is n minus UL. T will be the same. I think you remember what is n. N is W cos alpha. Right? N is, in the previous lecture we learned, is cos alpha, and T is W sin alpha, right? So we can put this in a table. So what we need to find first is, let's say, weight, right? Weight of the slice, right? So we know it's calculated by multiplying area with the unit weight 19. Okay. Then we know the weight. If we know the weight, we can find N and T components. So this is N and T. So to find N, it is W cos alpha. So this should be equal to weight cosine, again radians. If you are using calculator, you don't need to put the radians. This is for Excel, okay? Radians, this value. Right. for T, W sin alpha, using again radians. So we have n and t components. Now remember, last time I did a extra example that to for you to get your attention on this alpha. You can see here the alpha. Now this is the same alpha. Okay, if you take the horizontal, this is the same alpha. Okay? It's like having this is 90 minus alpha, so this is alpha, right? So this is the same alpha. So you can see it is reducing, alpha is reducing, right? Here it becomes, you can see 5, reducing 5, then it is increasing. Therefore, it should be in the other way around. This should be negative. This should be negative, right? So this should be put as negative value. You can see, right? So now we have both n and t components. So next thing we need is our u and l. Right? So I'm going to put another one. First of all, find L value, right? So L can be computed using this b over cos alpha. So I'm going to take b is the width divided by cosine radians of we need to, so that is L value. Then u, to calculate u is HW into gamma W, which is 10, so we can multiply this by or you can just write both u. Straight away I'm going to write the UL. Okay, so UL is HW, gamma W is 10 multiplied by L value, so we have UL. So therefore we have a new one, n minus UL, because what we need here is not n, what we need here is n minus UL, that is n dash, right? So we need sigma of L dash. You can see everything here is again sigma, right? So this should be equal to this minus UL, that is n minus UL. So if we take the sum of this, we get total n dash, and also we need the sum of this sin W sin alpha or t. So we have that too, and finally you can see there is a part C dash L, sigma of C dash L is in the same brackets, right? As you can see, there should be another bracket here, right? It is lost in the PDF, right? So sigma, what it says actually is should be sigma of all, right? Then C dash L n minus UL and T dash divided by sigma T, right? So once you take sigma, you have So each and everything will be become sigma. So UL so finally what we need is C dash L. So C dash L, what is C dash value? C dash given as 10. So 10 into L. So we need the sum again. So now we have everything what we need, and finally the phi value, tan phi value is given as 28. Now you can see we don't need this r and theta because we have found L values for each and every slice, right? So P dash is 28, right? So we can find the factor of safety. So it should be this plus n minus ul multiplied by tan radians 28. This part is separate. That is the top part, and the bottom part is this sigma t, right? So there are the factor of safety. So factor of safety should be this divided by this. So you can see we obtain 1.14, quite a low value of factor of safety, right, for this scenario. Okay, so I hope you understood how we process this, the process that we follow analyze the slope with respect to effective stress analysis. So in your handout there is a second part. So this today what we have discussed is effective stress analysis. This we call conventional method, right? So this method we call conventional methods or Bishop's conventional method, right? So the next thing is Bishop's rigorous method or routine or rigorous method, right? So the second page is for that. So this is the equation, right? So we'll discuss this later. As I told you earlier, at the first day of slope stability analysis, in the softwares what we use is this rigorous method, right? It is an iterative method, right? So I'll discuss this in our next lecture, right? So now you can go through this, and also I'll send you another example so you can try at home. So see you in the next lecture.